It is the 10th of May, 2024, and something is going wrong in the sky. Air traffic controllers across Europe are watching flight tracks jump and stutter on their radar screens for no reason anyone can explain. Farmers running GPS-guided tractors in the American Midwest suddenly find their machines drifting off course by several feet, ruining carefully planted rows in the middle of planting season. In orbit, engineers at satellite operation centers are scrambling as thousands of spacecraft begin unexpectedly losing altitude and drifting from their assigned positions, forcing emergency maneuvers to avoid collisions. And far above the planet, the night sky is doing something it has not done in living memory. Auroras, usually reserved for the far north, are blazing green, pink, and violet as far south as the Florida Keys, the Bahamas, and Puerto Rico. For a few terrifying, beautiful hours, Earth is being struck by the most powerful geomagnetic storm in more than 2 decades, and almost nobody saw it coming, at least not at this scale. Power grid operators from the American Midwest to Scandinavia were on high alert, watching voltage readings twitch as induced currents crept into transmission lines, the same kind of phenomenon that knocked out power to millions in Quebec back in 1989 after a much smaller storm. Nobody was panicking outright, but everyone with a hand on the world's critical infrastructure that night understood exactly how close things could get if the storm's magnetic orientation had been just slightly different. The culprit was our own sun, and this single storm was only a preview of something much bigger scientists had gotten badly, fundamentally wrong. Our star had entered its most violent, unpredictable phase in a generation, one that shattered our best forecasts and forced us to question everything we thought we understood about how the sun actually works, where its power comes from, and what might be coming for us next. Every 11 years or so, the sun cycles between 2 very different moods. There's the solar minimum, a quiet, dormant stretch when the sun's surface is relatively calm, and the solar maximum, an explosive, turbulent period when the star is at its most active and dangerous. Scientists have long used sunspots, dark, cooler patches on the sun's surface caused by tangled magnetic fields, as a rough gauge of where we are in that cycle. More sunspots generally mean more magnetic tension building up, and more magnetic tension means more solar flares and coronal mass ejections, the violent eruptions of plasma and radiation that we call solar storms. In 2020, the sun officially entered solar cycle 25. Based on decades of prior cycles and a formal 2019 prediction panel convened by NASA and NOAA, experts expected this one to be weak, forecasting a peak of roughly 115 sunspots, in line with the 3 previous cycles, each one weaker than the last, with cycle 24 ranking as the feeblest in 100 years. It was supposed to be an unremarkable, forgettable stretch of solar activity, the kind of cycle that barely makes the news. Nobody was expecting fireworks. Instead, cycle 25 exploded. By August of 2024, scientists counted 216 sunspots in a single month, nearly double what had been predicted, and the highest count in 23 years. The sun was almost twice as active as our models said it should be. And that raised an uncomfortable question nobody wanted to ask out loud. If our predictions were this wrong, what else don't we understand about our own star? To understand why the forecast failed so badly, you have to understand how scientists try to predict solar cycles in the first place. The most reliable method available is something called the polar field precursor. As sunspots break down over the course of a solar cycle, the magnetic flux left behind doesn't just vanish, it slowly drifts toward the sun's poles, gradually building up a strong magnetic field there. That polar field, measured at solar minimum, essentially seeds the strength of the next cycle. The stronger the polar field, the more powerful the following maximum tends to be. To actually measure it, researchers rely on instruments like the helioseismic and magnetic imager, a device aboard NASA's Solar Dynamics Observatory that has been staring at the sun from Earth orbit since 2010. It is, in theory, one of our best tools for peering into the sun's magnetic future. But in 2025, researchers at the National Solar Observatory built a detailed virtual model of that very instrument and ran synthetic magnetic field data through it to test its accuracy. What they found was startling. The real instrument appeared to have been detecting only about half of the sun's true magnetic field strength at the poles. Half. For years, one of our primary tools for forecasting solar activity had effectively been showing us only a fraction of the picture, and nobody had realized it. That alone helps explain why cycle 25 outperformed expectations so dramatically. But even accounting for that error, the cycle was still stronger than the corrected numbers suggested it should be, which meant something even deeper was going on beneath the sun's surface. For nearly 400 years, since the days of Galileo, scientists have puzzled over what actually powers the sun's magnetic activity. The long-standing theory pointed to a layer more than 120,000 miles below the surface called the tachocline, a boundary where different layers of the sun rotate at different speeds. The idea was that this differential rotation wound up magnetic field lines like tightening a spring, generating the dynamo that drives everything we see happening on the sun's surface. But in 2024, a team of researchers from MIT, Northwestern, the University of Edinburgh, and other institutions challenged that entire framework. Using a NASA supercomputer to run the most detailed solar simulations ever attempted, they found evidence that the sun's magnetic dynamo might actually originate far closer to the surface, at a depth of only about 20,000 miles, roughly 6 times shallower than the old theory proposed. If correct, it would mean the engine driving 11 years of solar violence sits roughly 6 times closer to the surface than generations of textbooks have claimed. This near-surface dynamo would be powered by something called magnetorotational instability, a process where a weak magnetic field links 2 layers of plasma spinning at different rates. Rather than smoothing out that difference, the magnetic field amplifies it, generating turbulence that feeds and sustains the dynamo. This mechanism would help explain why consecutive solar cycles can swing so wildly in strength, and unlike the old tachocline model, it produces predictions that can actually be tested against real observations. It's a genuinely uncomfortable idea for solar physicists, because it suggests the engine driving all of this chaos has been sitting in the wrong place in our textbooks for decades. To test ideas like this directly, scientists needed to get closer to the sun than any spacecraft ever had. In 2018, NASA launched the Parker Solar Probe, named for the astrophysicist Eugene Parker, on a mission to fly directly through the sun's outer atmosphere. After a roughly 3-year approach using multiple gravity assists from Venus, the probe arrived in April of 2021, just as the sun was beginning its climb toward this unexpectedly violent maximum. On Christmas Eve of 2024, it made its closest approach yet, skimming past the sun at a distance of only about 6 million kilometers while moving at nearly 700,000 kilometers per hour, making it the fastest human-made object ever built. But the speed record isn't even the most important thing it accomplished. Over dozens of orbits, Parker has been quietly solving one of the sun's oldest mysteries. Why is the corona, the sun's outer atmosphere, so much hotter than its surface? The visible surface of the sun sits at a scorching but comprehensible 5,500 degrees Celsius. The corona above it, somehow, reaches temperatures of 1 million to 10 million degrees. That shouldn't happen. Heat is supposed to decrease as you move away from a source, not increase by a factor of 1,000 or more. For decades, nobody could fully explain it. Back in 1988, the same Eugene Parker, the probe is named after proposed a theory that most of his colleagues dismissed outright. 11. He suggested that the churning, boiling convection cells on the sun's surface, called supergranules, could twist and tangle the magnetic field lines stretching up into the corona. As those tangled lines built up stress, they would eventually snap and reconnect in tiny bursts he called nanoflares, releasing their stored energy as heat directly into the corona. It was a compelling idea, but it was mocked and largely ignored for decades. Then, his own namesake spacecraft found the evidence. Data from Parker's onboard WISPure camera revealed that the solar wind, which looks like a smooth, turbulent fluid from Earth's distance, actually flows outward from the sun in distinct individual streams that mirror the exact size and shape of the supergranules on the surface. As the probe tracked these streams orbit after orbit, it found something strange folded into the magnetic field lines. Sharp, S-shaped kinks called switchbacks. These switchbacks appear to form when closed magnetic loops on the sun's surface collide and merge with open magnetic field lines stretching out into space, a process called interchange reconnection. Each of these events releases a burst of heat and flings solar material outward, both warming the corona and accelerating the solar wind, essentially the exact mechanism Eugene Parker described nearly 4 decades earlier, finally caught in the act. The Parker probe also upended our understanding of coronal mass ejections themselves. For years, scientists assumed CME material only ever traveled outward, away from the sun. But during that same December 2024 flyby, the probe captured something nobody expected: a cloud of ejected solar material curling back around and falling back toward the sun in a dramatic U-turn. According to NASA, this returning material can subtly alter conditions in the solar atmosphere, in ways that influence how future eruptions behave. Scientists had caught glimpses of similar inflows before, through older missions like SOHO and STEREO, but never with this level of detail. With this new data, researchers can now measure the speed, shape, and size of these returning clouds precisely, information that could meaningfully improve our ability to forecast future solar cycles and space weather events that could affect both astronauts and infrastructure back on Earth. But Parker's orbit mostly keeps it near the sun's equatorial plane, which means it could only tell part of the story. To really understand what drives the 11-year cycle, scientists needed to look somewhere almost nobody had ever seen clearly: the sun's poles. Because nearly every spacecraft in history has orbited within the same flat plane the planets travel in, we have only ever glimpsed the sun's poles edge on, like trying to read a clock face from the side. The European Space Agency's solar orbiter was built specifically to change that, using a series of gravity assists from Venus to gradually tilt its orbit higher and higher, above the solar equator. On March 23, 2025, it finally crossed 17 degrees below the equator and turned its instruments directly onto the sun's south pole, capturing the very first images of it in human history. What it found down there was chaotic and genuinely surprising in at least 3 distinct ways. The first surprise: a normal magnet has one clean north pole and one clean south pole, but for a period during this solar maximum, Solar Orbiter found both north and south magnetic polarities tangled together and coexisting simultaneously at the sun's south pole. A genuinely messy, disordered magnetic state. Out of that chaos, the sun eventually flips its entire magnetic field. North becomes south and south becomes north, a reversal that happens roughly every 11 years. That means it actually takes the sun 22 years to complete one full magnetic cycle, known as the Hale cycle, before settling back into its most orderly state during the following solar minimum. The second surprise came from Solar Orbiter's SPICE spectrometer, which mapped the speed of solar material moving through the transition region, a thin, turbulent layer of the sun's atmosphere where temperatures leap from around 10,000 degrees Celsius to hundreds of thousands of degrees almost instantly. By tracking the specific light signatures given off by elements like oxygen, neon, carbon, and hydrogen at different temperatures, scientists built the first ever velocity map of the sun's south pole, tracing solar wind directly back to its actual point of origin, rather than inferring it from measurements taken millions of kilometers downstream near Earth. The third finding tied everything back to why Solar Cycle 25 outperformed expectations in the first place. A paper published in November of 2025 using solar orbiter data suggested that the poleward migration of magnetic flux from decaying sunspots may be happening significantly faster than existing models assumed. That matters enormously because, remember, the polar field precursor, the speed and strength of that poleward drift during one cycle determines the polar field strength at the following solar minimum, which in turn sets the strength of the cycle after that. If flux is arriving at the poles faster than our models predict, then our forecasts for future cycles, including the next one, could already be significantly off before we've even started making them. Add it all up, and you get 3 separate reasons. Cycle 25 caught everyone off. GUARD, a flawed dynamo model that placed the sun's engine in the wrong location, an instrument that was silently missing half the polar magnetic field it was supposed to be measuring, and a poleward migration of magnetic flux happening faster than anyone accounted for. So if our forecasting has been this unreliable, what does a truly severe solar storm actually look like when it hits us? And how much warning would we really get? We already got a preview on that 10th of May in 2024. The storm began when the sun unleashed a coronal mass ejection, hurling roughly 1 billion tons of magnetized plasma directly at Earth. It took several days to arrive, but when it finally slammed into our planet's magnetosphere, it triggered one of the most violent exchanges of energy between the solar wind and near-Earth space in over 20 years. The resulting auroras were seen in the Florida Keys, the Yucatan Peninsula in Mexico, the Bahamas, Jamaica, Puerto Rico, and Hawaii, places that essentially never see the northern lights, with skywatchers posting photos that many astronomers initially assumed had to be fake. A month later, a faint red aurora was spotted over Japan, and scientists later determined it had stretched an astonishing 500 miles into Earth's atmosphere, far higher than expected, suggesting the charged particles involved carried more energy than previously believed. As beautiful as those auroras were, the storm itself was quietly dangerous. Earth is normally protected by the plasmasphere, a bubble of charged particles that helps shield us from incoming solar material. When a geomagnetic storm strikes, the pressure of the solar wind compresses that bubble inward, like squeezing a deflating balloon. Afterward, the plasmasphere is usually replenished by particles rising up from the ionosphere below. Thanks to a stroke of good timing, Japan's RSA satellite happened to be perfectly positioned to capture this collapse in unprecedented detail. A research team led by Dr. Atsuki Shinbori at Nagoya University recorded the plasmasphere's outer boundary collapsing from roughly 44,000 kilometers down to just 9,600 kilometers in under 9 hours, shrinking to about a fifth of its normal size. The lowest altitude ever recorded for the plasmasphere's edge since the Aracey mission began collecting data back in 2017, a collapse so dramatic that some researchers reviewing the numbers initially assumed it had to be a sensor error. That collapse left satellites in geostationary and medium Earth orbit dangerously exposed, including weather satellites, television broadcast satellites, and critically, the global navigation systems billions of people rely on every single day. At the storm's peak, interference with GPS frequency bands caused position errors, data dropouts, and tracking failures across global airspace, with hundreds of aircraft affected across Europe alone, their flight tracks visibly jumping on radar. Data released by the United States Space Force later revealed that more than 5,000 satellites had to perform emergency maneuvers just to avoid drifting into dangerous orbits or colliding with debris, an enormous, largely invisible scramble happening in orbit, while most people on the ground were simply enjoying an unusually colorful night sky, unaware that a single miscalculated maneuver up there could have added thousands of new fragments of debris to an already crowded orbital environment. The most alarming discovery, though, came after the storm had technically passed. Under normal conditions, the plasmasphere takes only a day or two to fully recover. This time, it took more than 4 days. Scientists eventually traced the delay to something called a negative ionospheric storm. About an hour after the solar wind struck, intense heating near Earth's poles churned the upper atmosphere violently enough to drag heavier gases like nitrogen and molecular oxygen up into regions normally dominated by lighter atomic oxygen. Those heavier molecules reacted with the atomic oxygen ions and depleted them, and that mattered enormously, because atomic oxygen ions are essential to how the plasmasphere refills itself. Normally, when a positively charged oxygen ion collides with a neutral hydrogen atom, it steals the hydrogen's electron, ionizing it and sending it drifting upward along magnetic field lines to help rebuild the plasmasphere. But with far fewer oxygen ions available after the storm, that entire replenishment process slowed to a trickle. It was the first time scientists had directly and conclusively linked a negative ionospheric storm to a delayed plasmasphere. Recovery, a discovery that reshapes how we think about the true aftermath of a major geomagnetic event. Not just the dramatic hours during the storm, but the days of lingering vulnerability that follow it. Vulnerability that satellite operators and grid engineers now have to factor into their emergency planning long after the auroras have faded from the sky. And the sun wasn't finished. Just days after the May storm, it unleashed a massive X-class solar flare, the most powerful category that exists, registering at X8.7, one of the strongest flares recorded in this cycle, though still far from the largest ever measured, an X45 flare recorded back in 2003, roughly 5 times stronger. For real historical perspective, though, nothing in the modern satellite era compares to the Carrington event of 1859, still considered the most powerful geomagnetic storm ever recorded, named after the British astronomer Richard Carrington, who happened to be sketching sunspots through his telescope at the exact moment the triggering flare erupted. That storm was so intense that telegraph operators around the world reported sparks leaping from their equipment, and in some cases, telegraph wires burst into flames entirely, even after operators had disconnected them from their power sources. Researchers today estimate that a Carrington-level storm striking the modern United States could cause anywhere from $600 billion to $2.6 trillion in damage and knockout power for somewhere between 20 and 40 million Americans, with restoration times ranging from as little as 16 days to, in the worst-case scenarios, as long as 2 years, depending entirely on how quickly damaged transformers and grid infrastructure could be replaced. Here's the part that should genuinely unsettle you. The amount of warning we would actually get before an event like that hits is terrifyingly small. The single most important factor in how damaging a coronal mass ejection will be is the orientation of its embedded magnetic field. If that field points southward, it has the highest chance of connecting with and overwhelming Earth's own magnetic field, unleashing a severe storm. The problem is, we cannot reliably measure that orientation until the plasma reaches a location called the L1 Lagrange point, a gravitationally stable spot roughly 1.5 million kilometers from Earth, directly between us and the Sun. By the time a spacecraft there detects a dangerous orientation, we would have somewhere between 15 and 60 minutes to prepare. Not days, not hours in most cases, just minutes. While Earth's thick atmosphere shields most of us on the ground from the worst radiation, astronauts don't have that luxury. A major solar event occurring while a crew is in space could sharply raise radiation exposure inside their spacecraft within minutes, exposing them to doses that would otherwise take months or years to accumulate on the ground. And cumulative exposure over a career raises long-term risks, including cancer and other health effects that can impair cognition and performance. For crews outside the protection of Earth's magnetosphere, on the way to the Moon, or eventually Mars, there's often nowhere to hide and no way to simply wait out the storm. This risk was taken seriously enough that NASA equipped every astronaut on the recent Artemis II mission with a personal radiation tracker. And the Orion capsule itself carries a system called the Hybrid Electronic Radiation Assessor, packed with 6 separate radiation sensors monitoring dose rates throughout the cabin. If levels spike, the system triggers onboard visual warnings paired with an audible alarm, giving the crew as much notice as possible to take protective action. So what is actually being done to prepare for the next big one? On January 23rd of 2026, NOAA's SWFO L1 satellite arrived at that critical L1 point, carrying advanced instruments to make continuous real-time measurements of the solar wind, thermal plasma, and magnetic field orientation, alongside a dedicated coronagraph built specifically to detect incoming coronal mass ejections. It's the first satellite NOAA has ever fully dedicated to round-the-clock operational space weather monitoring. Alongside it sits NASA's Interstellar Mapping and Acceleration Probe, also stationed at L1, working to deepen our understanding of exactly how space storms form and dissipate, aiming to improve real-time forecasting for the events still to come. Looking further ahead, the European Space Agency's Vigil mission, scheduled to launch in 2031, will take up a position at the L5 Lagrange point, off to the side of the Sun, rather than directly in front of it. From that unique vantage point, Vigil will be able to watch dangerous active regions on the Sun's surface rotating toward Earth before they ever come into direct view, potentially stretching our warning window from a handful of minutes to several days. On the ground, engineers and grid operators are racing to harden critical infrastructure against exactly this kind of event, deploying smart grid technology capable of detecting and isolating dangerous surges before they cascade, installing high-voltage surge protectors at key substations, building strategic reserves of spare transformers so damaged ones can be swapped out quickly rather than waiting months for replacements to be manufactured, and even experimenting with Faraday cage shielding around especially critical electronic systems to blunt the impact of electromagnetic pulses generated by extreme storms. Utility companies in several countries have also begun running dedicated solar storm drills, rehearsing exactly which transformers to disconnect and in what order if forecasters ever detect a Carrington-class event heading our way, treating it less like a hypothetical and more like the kind of disaster you plan for the same way you would a hurricane or an earthquake. None of it is foolproof, but slowly, and not a moment too soon, we are building the infrastructure to survive what our own star can throw at us. Solar Cycle 25 turned out to be a wake-up call disguised as a scientific curiosity. It exposed just how much we still don't understand about the mechanics of our own sun, forcing us to question the location of its magnetic engine, the reliability of our best measuring instruments, and the true speed at which its magnetic fields migrate toward the poles. But it also delivered an extraordinary run of discoveries. The very first photographs of the sun's poles, a serious challenge to a decades-old theory of the solar dynamo, direct confirmation of Eugene Parker's once ridiculed nanoflare theory, and the first conclusive link between a negative ionospheric storm and a delayed planetary recovery. Solar Cycle 26 is expected to begin sometime between 2029 and 2032, and if Cycle 25 taught us anything, it's that we should be very cautious about assuming we already know how strong it will be. What we do know is that we're heading into it with sharper instruments, better positioned spacecraft, and a much deeper respect for just how much our sun still has left to surprise us with. And this time, we may actually get the warning we need before it does.